All right, so we're looking at the second page here. It's a little cut off, but should be good. A little statement at the top. The final parent function that we want to examine is the basic square root function. All right, so we have y is equal to the square root of x. So the first little part of this problem, examine a table of values for this function. Why are there no inputs for when x is negative? So let me wipe out what I have here on Desmos. I'm going to put in, I'll write y equals square root of x. All right, so that's what our function looks like. You see no part of it goes to the left of the y-axis. All right, so no output values for when x is negative is because you cannot take the square root of a negative number. Down the line, you'll learn why that's the case, but for now, we just kind of accept it as a rule. The table of values, so again, you hit that little gear icon, tap on the table, and it'll populate a table for you. And you see, for the negative x values, you have undefined, but then you have the positive values that are all populated. So if I could put in decimal values, I could put in whole number values. I'll just put in a 3, 4, and a 5. You see some of them are nice and clean. Others are what they call messy. All right. If I put in like a decimal, so my next one, if I did like 6.1, still gives me a number. So decimal inputs are okay as long as they're non-negative, right? So they're going to be 0 or more. Why are many of the values in the y table, many of the y values in the table messy? That's because they're the result of finding the square root of numbers that aren't perfect squares. All right, now if I wipe out those values, so let me just take away that 5, take away the 3, the 2, and replace them with only perfect squares. So I'll put the 4, next one would be 9, 16. You see that they result in nice, clean y values. And if you look at the graph, you see that those points give us a good enough idea of the shape of the graph that we don't actually need the messy ones in the middle in order to create the graph. So 0, 0, 1, 1, 4, 2, and a 9, 3. And then if I could go further, then you'd have a 16, and you'd get 25 after that. But what we have here is part of a sideways parabola, right? So if I graphed the bottom half, you'd see that this would be essentially a parabola, but turned on its side, and there's ways to handle that. But for now, we just look at it as a set of perfect squares. All right, so we have our graph. I'm going to throw an arrow on at the end because it indicates that it's going on. All right, it's not just going to stop when the grid ends. Basic square root curve is half of what other type of curve that you've seen in this course, and again, that's parabola. I created the table of values in the Desmos, so if you want to write them down, you're welcome to, but not necessary. All right. For f, it's saying calculate the average rate of change for the function over the following intervals. Average rate of change, another name for slope. All right, so that's our change in y over change in x. Looks like we have our change in x. We need our change in y. Slope, as you probably have learned, we abbreviate with an m. All right, the m stands for modulus of slope, but that's more fun fact of the day territory because you don't really need to know that piece of information on the regents or anything. So my change in y or change in x, so I want to get the y value that corresponds with the 4 and an x value that corresponds the y value that corresponds with a 1. All right, so looking at my table here, I have an x value of 1 here, which has a y value of 1. I have an x value of 4, which corresponds with a y value of 2. All right, so these are my x values. So this 1 corresponds with this 1. All right, so this is an x, and this is the y. All right, the y value at the x value of 1. And it holds true also for this pair here. All right, again, this is an x value, and this is the y value that goes along with it. Then we can compute. So 2 minus 1 is 1, 4 minus 1 is 3, so 1/3. Doing the same thing over here. Again, we'll do the change in x on the bottom, so 9 minus 4. All right. The 9 has a y value of 3. The 4 has a y value of 2. So we're looking at 1/5. And what we have here is the idea that the rate of change changes. All right. So it went from a slope, and if I mark it on the graph, it was 1 to 4, right? So this line segment here, and it's kind of hard to see, but I just drew a straight line segment there. So we're going from this point to this point and connecting with a straight line, right? That second calculation was going from this point to this point. And again, if you connect it with a straight line segment, you can see it. Maybe it may not be as obvious with the scale, but the slope did get smaller. All right, so it went from 1/3 to 1/5 numerically, but in terms of the actual physical slope, like the slantiness of the curve, it got a little shallower. It was a little steeper earlier on. Now it's a little bit shallower. So when it says give an interpretation of what the values in f tell you about how the basic square root function behaves, we could write a simple statement like the slope decreases as the x values increase. All right, and it'll increase as the x values increase. The slope will decrease, eventually appearing to be a slope of 0, but it'll never actually get to a slope of 0. It's just going to look like it. You know, when you go to plot points, if you went out to like x equals 100, you're going to see that it looks very, very horizontal, but it's not precisely horizontal. All right, so we'll just say the slope decreases as the x values increase. Another statement here, like all the functions we saw at the beginning of the lesson, more complicated functions involving square roots certainly exist. This function here, and I talked about this on the previous page, if you have the parent function, it's really just a matter of moving some things around. So shifting left, shifting right, shifting up, shifting down, or stretching out the graph or shrinking it a little bit, all depending on what these other coefficients are. So the parent is y equals the square root of x. If I graph, so I have my parent function up on my display here. If I graph y equals f of x, I'll write it as f of x this time, equals to, we have our square root, x plus 4, then subtract off the 3. You can see it has the same general kind of feel. It's just a little bit bigger, and the starting point has been moved left and down. Let me just wipe away that 2 for a second. That's actually the same function that we started with if I were to take that endpoint, that left endpoint on the blue graph, well, I guess they're both kind of blue. Let me do this real quick. If I take that endpoint on the blue graph and move it down 3 and left 4, then I would have this new red graph. All right. when it says find the value of f of 0, we could do it graphically. All right, I can just type in my calculator, f of 0, get that number. All right, I could also plug it into this function for x, replace the x with a 0 and simplify. I'm going to get f of 0 is equal to -1. That's the y-intercept. All right, so y-intercept. All right, that's where it passes through the y-axis. All right, the way the question is phrased, what does this tell you about the graph? I mean, it's not the most elegant answer of saying, what does it tell you about the graph? Y-intercept. Okay, it's telling us the point at which the graph crosses the y-axis. But what is that? That's a y-intercept. So a nice, clean, concise way of saying it would just be to say y-intercept. Table of values of the function. All right, let me just pop this out of here. Again, looking only at the nice values. All right, but if you just go by what Desmos gives you as a starting point of the graph, you could run into trouble because, or starting point of the table associated with the graph. Because on this graph, I can see that there's a point in this neighborhood over here around -4. Right, but my table starts at -2. So let me change that, make it start at -4. All right, so at -4, I'm going to have a -3. And then after that, if you want to increment it, you know, by 1 unit each step of the way, you can. But remember, because it's a square root function, you're going to get a lot of stuff in there that you might not necessarily want. All right, so these values here, the -1 and -2, they're not clean, so I'm going to ignore them. All right, but at 0, I have my -1. Then if I go down the line, oops, 3 is not really clean. 5, that's a good one. And just keep going until I get another good one. At 12, I get a 1. So I'm going to have to kind of target that. So 12 would be over here. I can't really go off the grid, but I can aim for this point. All right. So when I draw my curve, I'm going to go through the x-intercept at 5, but I'm just going to kind of let it flutter there. Instead of just trying to lock it in on a point, I'm just going to throw an arrow because I need to be aiming for that location. All right? Even though it's off the grid, it's still something I can aim for. But then I'll wipe away all that stuff so I don't give the person grading it on the exam any reason to take off credit. All right. When it says what's the range of this function, the range, domain and range. Domain is all possible values for x. Range is possible values of y. All right. So looking at my graph, my very first y value starts here. Now, it's hard to see, especially with a graph that doesn't increase dramatically. And it does a little bit early on, but then it has a leveling off factor. This graph, if I were to go out to 100, it would get up as high as, in the neighborhood of 10. If I go, actually, I could put some values in there. 100, close, it's around 7, but, in the neighborhood of 10. And let's say I put 1,000 in, I'm up to 28. Put a bunch of zeros there. I'm up to 1,000. All right. The short answer, I guess, is that it really never stops increasing. It's kind of hard to see on this touchscreen, but this value here, if you look on your own screen, right next to this 100,000, this number here, you see you have times 10 to the 7th power. That's scientific notation. It tells us to take that decimal point and slide it to the right 7 times. So that's a really huge number is the the short version of that explanation, right? So the idea is that this is never actually going to stop increasing, right? It's going to increase forever. So it starts off, your y values for your graph start off at -3, and they never stop. The graph never stops increasing. So there is no upper bound, right? So starts at y equals -3 and never stops increasing. All right. The way we write that mathematically is to say, for my range, R for range, little colon indicating that I'm about to tell you what the range is, y is going to be greater than or equal to -3. All right. That's telling me that my lowest possible value of y is -3, and it never stops increasing after that. So there is no upper limit. All right. So now you should be able to move on to the fluency, and then you can, if you have time and you want to look at it, you can start looking at page 6 too. But really, the idea is for you to get through page 5 today.